Ngalakin Khadijan Nyunga Boja.
Stuart, are you logged in or not? You just can't see, is it? You can see the screen? For those who are joining us online through Zoom, are you able to hear me? And also, are you able to see the slides? Okay, great. Thanks. Good evening, everyone. We'll continue this lecture from where we left last week. We spoke about real transformers, the equivalent circuit for a real transformer, and the tests that we need to perform to identify its parameters, right? We know the equivalent circuit for a transformer has a shunt branch. So there is some shunt admittance, and it has a series path, so there is some series impedance, right? We talked about that in detail, but to identify the parameters, we need to identify the shunt admittance and the series impedance. Now, we perform two tests to identify the parameters of a transformer. The two tests are the open circuit test and the short circuit test. The open circuit test will allow us to determine the shunt admittance. The short circuit test will allow us to determine the series impedance. So in both tests, we actually make three measurements. We make a voltage measurement, we make a current measurement, right? In the open circuit test, we measure the open circuit voltage. We measure the current that will flow through the shunt branch, right? And we will also make a power measurement. So three measurements. And we do the same for the short circuit test. With the short circuit test, obviously the current measurement is the current that flows through the series impedance. We'll measure the voltage, the terminal voltage across the transformer, and we will also make a power measurement. So in both cases, we make three measurements. Yes, you have a question?
Is it, when you're doing a short circuit or open circuit test,
yeah.
Is it ever possible to find any of those values, like power, voltage, or current using the rated values that are given about the transformer and
Yeah. Basically what you do is, for the open circuit test, you open the terminal, the secondary terminal, and then you apply a voltage. And that voltage that you apply on the primary, right, will appear will appear across the shunt branch because there is no current flowing through the series impedance, right? And that voltage in a short circuit test, that voltage that appears will appear across the series impedance because we assume that no current flows through the shunt branch, right? Yeah. Yeah. No current flows through shunt branch is an assumption that we make when we do the short circuit test. Right. So we are making three measurements, right? And we know this formula, Vi cos theta is equal to P, right? So we measure the magnitude of V, may measure the magnitude of I, we measure P, right? So we can compute theta. Theta is the angle, right, between voltage and current. So in the open circuit test, then we can actually determine the shunt admittance, right? The magnitude of the admittance and the angle, because the magnitude of the admittance is the magnitude of the current divided by the magnitude of. Can I ask the audience to please put your mics on mute, because otherwise, we hear you talking. So kindly put your voice on mute. And if you have any questions, please type it in the chat box. Otherwise, it will interrupt my lecture here, and also those who are present here face to face. So so I kindly request you to put your mics on mute. All right. So getting back to the open circuit test, right? Open circuit test will determine the shunt admittance. So the magnitude of the admittance is the magnitude of current over magnitude of voltage. We make those measurements, so it's there. We can determine the angle theta, and it's the negative value of that is the angle of the admittance, and we talked about that. It's pretty straightforward. And with the series parameters, again we make the same three measurements. So the magnitude of the impedance is magnitude of voltage over magnitude of current. Same thing, it makes sense. And the angle theta for the impedance is the angle that we compute using the power measurement. P equal Vi cos theta. So it all makes perfect sense. And we looked at, that we discussed in the last lecture. We looked at an example, right? So we have the same three measurements, the open circuit voltage, open circuit current, the power measurement, the short circuit test, the same three measurements, right? We have those things, and we determine the shunt admittance and the series impedance based on what I just said, right? Straightforward. We looked at that in the last lecture. And once you know the admittance, right, and the impedance, notice that the admittance and the impedance is going to be in polar form, right? Is in polar form. So if you write it in Cartesian form, right? Here is the polar form. You can see the polar form, right? This is the polar form. Let me highlight it. This is the polar form for the shunt admittance. We can write it in Cartesian form. So Cartesian form will have a real part and an imaginary part. And the real part is the conductance. Imaginary part is the susceptance. And then you know the two parallel elements in the shunt branch, right? And the same thing can be said once you determine the series impedance using the short circuit test. It's in polar form. We can translate that into Cartesian form, and then the real part is the resistance, imaginary part is the reactance, right? So we have two elements connected in series, in the series branch. So this should be very clear to you, right? Very obvious, very clear to you, and it's quite important that you know this well. Here is the equivalent circuit, the two parallel elements in the shunt branch and two series elements in the horizontal branch. Right. Okay. And this is the transformer reflected to the primary part. So Vp appears on the left-hand side, A times, A is the turns ratio times voltage, because voltage, when you take it from the secondary to the primary, you multiply by A. Current, when you take it from the secondary to the primary, because this circuit, what you see here, is reflected to the primary, so the current, the secondary current, has to be divided by the turns ratio. Primary, secondary voltage multiplies by turns ratio, right? So that's something to keep in mind as well. And we talked about this phasor diagram, right? So when you I said that you need to have the ability to take a clean sheet of paper, right? Draw the equivalent circuit for the transformer, which is on the top right, right? So we have nothing. You can draw the equivalent circuit. Once you draw the equivalent circuit, you should be able to actually start drawing the phasor diagram. And how do you do that? You actually choose your reference voltage to be the secondary voltage, to be the reference. So that horizontal line that you see here, this horizontal line that you see here, that's our reference. It's the secondary voltage. It's a voltage that appears across the load. So we got to have a clear understanding of, when we're talking about voltages, where this voltage appears. It appears across the load that is connected to the secondary terminal of the transformer, right? And then if you have a load, and then we know the current that flows through the load depends on what is connected, the load, whether it's a resistive load, whether it's an inductive load, whether it's a capacitive load. If it's an inductive load, the current will lag the voltage, which is the condition that we have assumed here, right? So from that, we can then determine the voltage drops across the resistor and the inductor in the series branch, because if you know the current that flows in the load, it's the same current flows in the resistor and the inductor in the series branch, and the voltage that appears across the resistor then is parallel to the direction of current, is parallel to the current phasor, and the voltage that appears across the inductive element will be perpendicular to that with 90 degrees leading, right? So these are this vector and this vector, right? The voltage across the resistor and the inductor. And if you sum them, that's the voltage in the primary terminal of the transformer, which is this vector here. And once you know that, you know the magnetizing current is perpendicular and it's lagging. That's Im, and also the current that flows across the conductance is parallel to that voltage that appears across the primary, and then that's the current that's flowing in the shunt branch. It's the sum of the two. So you should be, I've talked about this in the last lecture, you should be able to draw this by yourself, right? Draw this by yourself. And all the drawing sequence is actually outlined here from steps 1 to step 7. Okay? And then we talked about voltage regulation. I think, see, for you to have this understanding of what these formulas mean, even though this formula will be given to you in a formula sheet, I mean, it will not make too much sense unless you understand, unless you can have a picture of the transformer, of the voltages where they are. It doesn't make too much sense. So I want you, I talked about this, I'll tell it again. Firstly, full load. What is the full load? When you apply the rated voltage, right, and the rated power, because when you know the rated voltage and the rated power for the transformer, you know the rated current. That's the current that flows in the load. And if you're given the power factor for the load, you know the angle of the current because you take the voltage as your reference, right? So you know the power factor of the, if you know the power factor, you know the angle of the current. And so full load is the rated load, and you know the angle of the current that flows through the load. You can determine what is the voltage at the input of the transformer, because you know the equivalent circuit. You can determine, and now if you were to all of a sudden disconnect the rated load, or then that voltage at the input of the transformer will appear at the output. So that is what we call no load voltage. So you could imagine that the no load voltage will be higher than the rated voltage, because that all of a sudden that higher voltage that appears across the terminal will appear at the load. On the load side across the terminal, there is no load now, right? So it will be higher, and the voltage regulation is the ratio of the no load to full load over full load. So you could now imagine, so if you have what is this voltage regulation, you could imagine what it is. You have a rated load, you have some current flowing, right? And then imagine all of a sudden you keep decreasing this current. When you keep decreasing this current, the voltage at the output of the secondary will keep increasing, right? Until you entirely take out the load, the current will be zero, and the voltage will be the highest. So voltage regulation is the voltage variation that you see at the output of the transformer as you change the load current. So have this picture in your mind, so then these equations make a lot more sense. You have a greater in-depth understanding of what's happening. Yeah, so that's what is needed. And then we talk about the efficiency of the transformer, because we know there are resistive elements in the equivalent circuit of the transformer. There is winding resistance, right? In the series branch, there is a resistance in the shunt branch, or conductance or resistance, right? So we know where they come from. Winding resistance come from the resistance of the windings in the transformer, and so on. So we talked about that. So there are going to be losses in the transformer. So the output power, so everything that you put into the transformer, the input power does not appear at the output because there are some losses. So what appears at the output is the input power minus the losses in the transformer is the output power. Output power, input power is the efficiency of the transformer, right? So did we go through this example? All right, so I won't go through the numbers, because the number calculations, multiplications, divisions you can do. I'll just outline the concepts so that you have an understanding. Right, so here we have a real transformer, 15 kilovolt amps, so that's the apparent power rating, 230 volts. So when I read these two numbers, now this is important, when I read these two numbers, you must immediately be able to imagine the rated current. In other words, if you now connect a load into the secondary terminal of the transformer, what is the current that's going to flow? Rated current. So the rated current will be the rated apparent power, which is 15 kilovolt amps, divided by 230. That is the rated current that will flow through the load of the transformer. So that immediately has to strike your mind when you read this, the numbers, right? And then we do the two types of tests, right? Two types of tests, the open circuit test and the short circuit test, right? From that we can determine the transformer equivalent circuit parameters. I'm not going to go through that. I've talked about it. You know how to calculate that using these numbers. And then, okay, the first part is to find the equivalent circuit. Second part is find the equivalent circuit of the transformer, referred to the firstly part A, high voltage side, and then to the low voltage side. So these tests are performed on the high voltage side, right? So the series impedance shunt admittance that you get are the values relevant to the equivalent circuit referred to the high voltage side. Now if you want to translate those into the low voltage side, which is the second part, so you need to divide all those impedances by the turns ratio squared, right? Turns ratio squared. So here is the equivalent circuit. The top part is the equivalent circuit refers to the high voltage side, primary. To refer it to the secondary, you take all the elements. You can see 4.45. You divided that by turns ratio squared. So what is the turns ratio for this transformer? N1 on N2 is V1 on V2, which is in this case, right, single phase, is 100, because 2,300 divided by 230, which is which is 10. It's 10, right? So turns ratio is 10. V1 on V2 is N1 on N2. N1 on N2 is the turns ratio. So then turns ratio is 10. Turns ratio square is 100. So we divide all these element values by 100 to refer it to the secondary terminal, right? So you can see 4.45 has been reduced to now 0.0445 because we divided by 100, and all same applies to all the other elements. Right, okay. So the next thing, okay, what is the next question? Next question is calculate the full load voltage regulation at 0.8 power factor lagging, 0.8 power factor, unity power factor, and 0.8 power factor leading, right? So we want to compute the voltage regulations when we have three different types of loads. One type of load is 0.8 power factor lagging load. The other one is a unity power factor load. Other one is a 0.8 power factor leading load. Three different types of loads, right? So we know the rated current, right? We know the power factor. So if you know the power factor, we know cos theta is the power factor. We can calculate theta, right? Whether it's a leading or lagging, theta is going to give you the, cos theta is going to present you a positive number, right? So lagging means the current lags the voltage. Leading means the current leads the voltage. Unity power factor has a 0 angle, right? So with the power factor, we know the current. We know the magnitude of the current, and we know the angle of the current. Why we know the magnitude of the current? Because it's a rated current. We know the rated power, we know the voltage, rated voltage, we know the rated current. So with that, we know the angle. So with the angle, we can calculate what is the no load voltage. We can calculate. No load voltage is a voltage that that appears across the load, right? No load voltage. No load voltage will be the rated voltage because that's a full load voltage, rated voltage. Now, I beg your pardon, I confused you. Full load voltage is a rated voltage. No load voltage is the voltage that will appear at the terminals when you take out the load. Yeah? Full load voltage is a rated voltage. No load voltage is, there is no load. I have taken out the load. So whatever at the terminal of the input terminal of the transformer will appear at the output of the transformer, right? So we can, because we know this current, right? We can compute the voltage at the input of the transformer, right? Because Vs in this situation is going to be the rated voltage that appears across the transformer, which is 230 angle 0, right? The current, the lagging power factor case is this amount, which is this amount, which is the rated current, and the angle is negative because it's a lagging power factor, right? And that's when you multiply with the series impedance, you get the voltage drop across the series impedance, right? This is the voltage drop across the load because we have a rated load, so rated voltage appears across it. So this thing here is the voltage at the input of the transformer, which is what appears here, right? Which is what appears there, yeah? But we have a load now. So that's the full load voltage. Full load voltage is this rated voltage. It's the voltage that appears across the load, yeah? Full load voltage. Full load voltage is going to be 230, right? No load voltage is this guy, is whatever we calculate here, because now if I take the load off, this 234.85 is going to appear across the output of the voltage. This 234.85 is what appears here at the input, right? Now if I all of a sudden take this load off, it's not there. This this input voltage is going to appear at the output. Yeah. So that's that 234.85, right? So no load minus the full load divided by full load is a voltage regulation, right? So that's for one type of load, which is the lagging load, right? For leading load, what do? You do the same calculation. But of course, this angle here is now positive 36.9 instead of negative, because 0.8 power factor leading, current leads the voltage, right? And you do the same calculation, right? And you calculate the voltage of the transformer at the input terminal, right? And then you can calculate this voltage regulation. And for unity power factor, you do the same calculation with this angle being 0, because the angle is 0 for unity power factor. Repeat the same calculation, and the calculations are repeated here, right? So here is the lagging case with the phasor diagram drawn, right? This is the unity power factor case. Unity power factor case, the secondary current is actually parallel to secondary voltage. This is the secondary voltage, this is the secondary current. Yeah. And this is the leading case. This is the secondary voltage, this is the current in the load leading that voltage. Okay. So we have this phasor diagram. We can do all these calculations and find the voltage regulation. Okay. All right. So I'm not showing you the calculation because it doesn't make any sense. What makes sense is the understanding that I'm describing to you, which will help you to understand the numbers. All right. Yeah. All right. So the next part is we need to calculate the copper losses, right? Efficiency of the transformer. To calculate the efficiency of the transformer, for which case, because we need to calculate which case we are considering, which power factor. So let's go back and have a look. What is it talking about? Okay, for the 0.8 power factor lagging case, okay, sketch the transformer phasor diagrams. We've done that. What is the efficiency of the transformer at full load with a power factor of 0.8 lagging? Right? Again, the fact that it's full load tells us what is the current that's flowing in the load. 0.8 power factor lagging, I know the current magnitude, I know the current angle, right? I know that. Rated voltage means the voltage across the load is 230 on the secondary side, right? On the primary side, it will be 2,300, right? If the circuit is reflected to the primary, yeah? And then I can calculate now. I want to calculate the efficiency. So how do I calculate the efficiency? I need to know the losses, right? What are the losses there? There are I squared R losses in the series branch. So if you take the magnitude of the currents in the series branch, square that, multiply by the resistance, that's the copper losses. Then we have core losses. That's the losses in the conductance in the shunt branch, right? In GC. Right, core losses. So we know the magnitude of the voltage that appears across the shunt element, right? Magnitude of the voltage. We can determine that, we know that voltage. So if you take that voltage, you square it, right? So here you can see here, it's Vp on A squared, Vp on A squared, Y divided by A, because we are looking at the equivalent circuit on the secondary side, right? Secondary side, and we have calculated that voltage. If you look through the calculations, you calculated that to be 234.85, right? Squared divided by the resistance in the shunt branch, divided by the resistance. We know the conductance resistance is the inverse of that. So you can compute these two losses. So the losses in the transformer are the copper losses, which is due to the windings, primary winding resistance and the secondary winding resistance. We have the core losses in the shunt branch, right? Losses in the core. And then if you sum them up, these are the total losses. So the output power is the input power, whatever you put in, minus the core losses. The input power we know. How do we know the input power? Because we know the input voltage, right? Input voltage. You know the current that is flowing through that. So how do you find the input power? VI cos theta. We know the voltage, we know the angle of the voltage, we know the magnitude of the current, we know the angle that flows through that, right? So the difference, angle of the voltage minus the angle of the current is theta, right? So VI cos theta, magnitude of V, magnitude of I cos theta. So what am I talking about? You need to be very clear, right? For input power, right? Input power, input is connected like that, right? So we know this voltage. We know that voltage. This voltage we know. We know this angle, theta. I'll call it theta. You have determined that already, right? You have, because we are connecting a load here. And we know it's a rated load, rated current is flowing through. So we have determined this voltage, we have determined this theta angle. We also have determined this angle I and angle gamma. We have determined that. So what is the input power? Input power in this case is V, right? This V is a magnitude. I is a magnitude. It is this current I, right? Cos theta minus gamma. All those parameters we know. All those values we know. How do we know? We calculated. Yeah, we have. So the input power we know. We have just calculated the losses. So the difference between input power and the losses is the output power. Now, if you want to do a double check on your output power, you can calculate this V here. You know that it's a rated value. It has an angle 0. You know the current here. And you know the power factor of the load, so you know the angle of the current. So if I now do secondary, I just call it IS and VS. I just call it that. So if I do now VS, this is angle 0. So if I do VS, IS, cos theta, that will be the output power, which must equal the input power minus the losses. That's a check that you can do to make sure you've done your calculations correctly, and divided by the input power will give you the efficiency, right? So I don't want you to show this complex number multiplied by this complex. I'm trying to explain you the concept, the understanding. You can do the number crunching, right? So what are the key messages? Key messages is you're given a rated power, a rated voltage. From that you can find the secondary current. You will be given a power factor. You know the angle of the current. You know the parameters of the circuit. You can determine all the voltages and currents everywhere, right? And you know VI cos theta is the power across an element. And if you know those things that I just said, you're set to do this type of question. Yeah? And you can practice that. You just look at a couple of examples and you know it, right? So that's what you need to do. Okay? Yeah? All right. And please be familiar with how to draw these phasor diagrams. That's important as well, right? That demonstrates your understanding. Yeah. So, getting on top of this unit, you require to turn up to lectures or at least listen to it online, or in the very worst, listen to the recorded in the 360 echo, and continuously, just based on the understandings that I'm trying to present to you, you actually do some examples, you will be on top of things. And I ask you to do that. All right. So now I'd like to talk to you about the per unit system. So what is the per unit system? Because, okay, what are the things that we talk about when you talk about an electric circuit? When I talk about an electric circuit, we talk about apparent power, S. We talk about impedance, Z. We talk about voltage, V. We talk about current, I. So I can just talk about these four things: apparent power, impedance, current, and voltage. So per unit system is about normalizing these values, normalizing. So what does normalizing mean? Normalizing means you have some base value for each of those four parameters, right? A base value, and you divide the actual value by the base value, so you have a normalized value. and the normalized value is the per unit value. Per unit value is a normalized value, right? So quantity in per units, you can see this equation, quantity in per units is the actual value, like for example, if it's volts, 10 volts, let's say it's the actual value, divided by the base value for voltages, which you choose, you're free to choose that, let's say 100 volts. Say you chose the base value to be 100 volts. So if I take the actual value 10 volts divided by the base value which you've chosen, which is 100 volts, then I have a per unit value of 0.1. Right? Per unit value of 0.1 for voltage. So what is the per unit values? Per unit values is a normalized value. Right? So to normalize, you need the actual value. You need to have chosen a base value, and if you divide the actual value by the base value, you have the per unit value. Right. It is customary to select two base quantities to define a given per unit system, which usually are voltage and apparent power. It doesn't have to be these two, but you choose two, and I'll explain to you why you have to use two. Right? You only choose out of the four that I talked about, apparent power, impedance, voltage and current, you only choose two. Because once you choose two, the other two are already determined. Because, right, S is equal to VI. Right? S is equal to VI. So if I chosen V and I as my base values, the base value for S is already predetermined. Because S base will be V base times I base. Because if I did something else, it wouldn't be consistent, wouldn't make sense. If I chose V and I as my base values, Z base is determined because V base on I base is Z base. Right? So we can only choose two. So while it is customary to base quantities to define a given per unit system, which is usually voltage and apparent power. Because if I then take the apparent power and divide by voltage, apparent power base value, voltage base value, I'll get the current base value because apparent power is the voltage base times current base. Right? Okay? So, theoretically, the base quantities can be arbitrarily chosen. Base quantities can be arbitrarily chosen. You can choose whatever you want. Right? Theoretically, the base quantities can be arbitrarily chosen for the purpose of facilitating the analysis of the power system. But in real world situations, base voltage and apparent power are chosen in accordance with the transformer specification in the power system. So the base values for base apparent power and base voltage will be chosen based on transformer rating. Remember the question that we did? We had a base apparent, it had an apparent power rating and a voltage rating for the primary and a secondary. So you can see the voltage rating for primary is different to voltage rating on secondary, right? So there is going to be a voltage base on the primary side. There is going to be a different voltage base on the secondary side of the transformer. So the base quantities on the primary and the secondary are going to be different for voltages. Base quantities for current is going to be different on the primary side to the secondary side, right? But what is going to be the same base quantity on the primary and the secondary is the apparent power. Because apparent power is the same on the primary and the secondary for the transformer. Isn't it? It's the same. Okay? So, while the base quantity is arbitrarily chosen, but in practice, this is what you do. You choose it based on the rated value. So, you know what percentage of the rated values you're talking about in per unit system. The apparent power remains constant everywhere in the power system, right? Base calculations are given here. So think about a single phase, right? Single phase means, okay, you only have one circuit. You have the active line, you have a voltage source, you might have some impedance on the transmission line, Right? You have a load. Okay? You have a circuit like that, single phase. So, and you can have transformers connected here. You can have a transformer on the generator side. You can have another transformer on the load side. Yeah? You step up before transmission, you step down before utilization. So you can have that situation. So this is the ground point, this is the neutral point, right? This is the active point, right? Some voltage. So let's focus on those equations on the left hand side. So that makes sense. The base apparent power must equal the base voltage times the base current. That makes sense. Z base is a voltage base over current base, right? So Z base also voltage square on power. Because if I substitute for current here, if I utilize the first equation, substitute in the second equation for current. So I base becomes S base divided by V, and the V then goes to the top to make it V squared. Right? So those equations are consistent. They are consistent. Those equations are consistent. So let's look at, so that's single phase. Right? So let's look at this right hand side. So the right hand side, the equation refers to three phase. So if I have three phase power, if I take three phase power as the base, three phase power, you know three phase power is, the apparent power is root 3 line to line voltage and times line current. So if I choose line to line voltage here as the base, then I base is going to be that. Yeah, I base is going to be that, because S is equal to root 3 times the line 2 product of the two line quantities. Now what is Z base? Z base is like we assume a star connection. We assume a star connection on the load. Assume a star connection on the load. Okay? Assume based on that. Writing these equations thinking it's a star connection. Then Z base is, okay, what is the voltage that appears across the impedance Z? Would be the line to line voltage divided by root 3 divided by current. So then Z base can be computed like that based on that equation. Right? Yeah. And then if I take the first equation for I base, substitute that in the second equation, right? We have this equation for I base, this one. Substitute that here, then we obtain this equation, third equation. Right? So if you are talking about three-phase circuit, you are going to use three-phase apparent power as your base, line-to-line voltage as your base, and you're thinking of a star connection, then these equations hold for base quantities. Right? Yeah? Okay. Reasons for using per unit system. Calculations are simplified because quantities expressed in per unit do not change when they are referred from one side of the transformer to the other side of the transformer. Now imagine you have your equivalent circuit for transformer, and the equivalent circuit for transformer, we have different element values. We have the impedance values, one set for primary side, and then you can reflect from the primary to secondary by dividing all the elements by turns ratio squared, right? So the element values change, but if you express those parameters in the per unit system, the values on the primary side and the secondary side is going to be the same. You can try that. They are going to be the same. The per unit values are going to be the same in the equivalent circuit. But remember, the base values on the primary and the secondary are different, right? Except for the base apparent power. Base apparent power is the same on the primary side and the secondary side, right? But the per unit values are going to be the same for equivalent circuit referred to the primary side or equivalent circuit referred to the secondary side. So what I will do as an exercise, right, I will take the examples that we did, choose those rated values as the base quantities, and then check the equivalent circuit referred to the primary and secondary to see if the per unit values are the same. Check that as an exercise. It will be the same. And you can also think why it is the same. All right, per unit system, continuing. We see a transformer. Number of turns on the primary is A, secondary 1, well, ratio is A to 1. Turns ratio is A. On the primary side, which is the left-hand side, the base value is V base 1. It will be the rated voltage on the primary. Can be. Then on the secondary, it's V base 2. It doesn't have to be, we don't have to choose it, the base quantities, the rated values, but we can. Right? If we don't, it doesn't matter. But yeah, it doesn't matter. So S base 1, S base 1 on the primary, S base 2 on the secondary, the base value, but they are the same. S base 1 equal to S base 2. We know that V base 2, which is the voltage on the secondary, we obtain by dividing the voltage on the primary by A. V1 on V2 equals A1, N1 on N2, right? Yeah, that equation. For the ideal transformer, we have the turns ratio equal to the ratio of the voltages. So you have V base 2 equal to V base 1 on A because of the transformer equation. And then we can write these equations. We can write this equation here, right? How do we write that? How do we understand that? S base 1 must equal VB1 times IB1. You would agree? SB2 base value 2 would be VB2 times IB2. You would agree with that? Then I can write SB2, from these two I can write SB2 on SB1, right? Must equal, so this divided by that must equal VB2 on VB1, IB2 on IB1. Okay, so I have IB2 must be, well, I can take this and that across like that, this across like this to the top, and then I have this equation, right? I have that equation. We can do the same thing to arrive at this equation too, because here if you eliminate I, yeah, S base is the same. If S base is the same, we can substitute that, but this is a general formula. This is a general formula, right? If you were to change the, well, it's a good question that you ask. This is a general formula, right? Of course, we can assume for transformer, we can choose S base 1 to equal S base 2, right? S base 1 is equal to S base 2. It is equal. And then we can substitute that, we can do that. But this formula that I've written here is a general formula. Now you might ask why I wrote that. There's a reason. The reason that I wrote that formula, this one, if you have base values, if you have per unit values referred to a particular base, right? per unit value refer to a particular base. I want to now change the per unit value to a different base. So S base 1, V base 1, Z base 1 is one set, one consistent set, right? But I told you that base values are arbitrarily chosen. But we can only choose 2 and the others are determined, other 4 quantities. But the per unit values will change if I change the base. Yeah? If I change the base. Because imagine like this. I choose the voltage base to be 100 and the actual voltage is 10. Per unit value of the voltage is 0.1. I can now choose a different base. I choose the base, instead of being 100, I choose the base to be 50. Right? Actual value is still 10. The per unit value is now 0.2. Right? Okay? So there can be one set of base, which is VB1, IB1, SB1, and ZB1. There can be a second set of base, which is SB2, VB2, IB2, ZB2. Suppose that I have the per unit value, right? Suppose I want to change the base. If I want to change the base from one base to another, I could use that equation. These 2 equations that you see here can be derived. It's derived based on the formulas that we know that are applicable for circuits, and we could use that to change the base values. So imagine, let's look a little more deep into this, right? Let's look a little bit more deep into this. Suppose that I have base values, right? So I have S base 2 and V base 2. Right? Suppose I have S base 2 and suppose I have that. So for a given base, there's only 2 parameters that we define. Right? Same thing. I have for base 1, I have S base 1 and V base 1. Let's say, right? And that will determine what that is. Yeah, that will determine what that is. This will be determined by those 2. And then if I want to then compute I base 2, I could use this formula to calculate I base 2. Yeah, I could. So I just plug in those numbers and I can get the current base for the second set. Yeah, you could. If you know V base 2 and S base 2, you can determine I base 2 as well. Yeah. So it'll turn out constant, but we will see how to use this formula. Because if I want to change some values from one base to another, right? If I know the base values for voltage, let's think about voltage. If I know the actual value, if I know the base, I know the per unit value. So if I know the per unit value at the base, I want to convert to a different base, I can do that by first calculating the actual value, right, from the first set of equations, and then jump to the second base. Now I have the actual value, I know the base voltage, then I can calculate the per unit value in the second. But instead of calculating the actual value, we can do a shortcut. You understand what I'm saying? Yeah? Because if I have the per unit value as the base, I can calculate the actual value. Then I take that actual value into the second platform. I have the different base values. I can calculate the per unit value after that. But we want to also short circuit the computation of the actual value without having to compute the actual value. All right. So but at least for now, these equations, where these equations, 2 equations came from, you should know, because I showed the derivation. Yeah? At least, where it came from. All right. for now. So, per unit system, example, a simple power system is shown below, which is this. This is the power system, simple power system. This system contains a 480 volt generator connected to an ideal 1 to 10 step up transformer, 1 to 10 step up transformer, a transmission line in the middle, and 20 to 1 step down transformer connected to a load. Right? A transmission line and ideal step down transformer connected to a load. The impedance of the transmission line is 20 J60 and the impedance of the load is 10 angle 30. The base values for this system are chosen to be 480 volts and 10 kilovolt amps at the generator. So the system contains 480 volt generator, right? So we have now chosen at the generator, that's the base value at the generator. We have also chosen, so this is the 480 volts at the generator, yeah. We have chosen that as the base value at the generator, and we have chosen 10 kilovolt amp as the apparent power base. Okay. Now the apparent power base is the same everywhere in the network. Apparent power base doesn't change. Now we have chosen the voltage base at the generator, but we know from one side to another side of the transformer, the voltage base changes. We know, right? We know that. So let's have a look. So here you are talking about this side of the transformer, generator side of the transformer. So voltage base is 480. We chosen that. S base, we have chosen that. Yeah, those are on the generators, on the left hand, on the generator side of the transformer. Now, to the right hand side of the transformer, on the transmission side, S base doesn't change. S base is the same. Now, the voltage base on the right hand side of the transformer will be different, right? So, the turns ratio here is 1:10. So, that will be the voltage base on the right hand side, because secondary voltage, V1 on V2 is N1 on N2. If you apply that, then we have this secondary voltage to be 4,800 volts. Right? V1 on V2 must equal N1 on N2. So V2 is V1 on A. Yeah? And V1 on A is 1:10, so we have 4,800. So we have computed these two values now. So we have these two values. To the right hand side of the transformer, we have the two base values. Because once you have two base values, the other base values are determined. The current and the impedance base values are determined, right? Using basic circuit equations. Same thing here. The current base and the Z base is known now. Right? Is determined. So then, on the load side of the transformer, this transformer, what are the base values? The transformer turns ratio is 20 to 1. Right? On the left hand side, we have V base is 4,800. So again, using V1 on V2 equals N1 on N2, where N1 on N2 is 20, we can calculate V base to be 240. Right? V1 on V2, so V1 would be 4,800. V2 is what we want to determine, equals N1 on N2. N1 is 20, N2 is 1, and then we can determine the base value to be 240 volts. S base is apparent power base, is the same everywhere. So this is we calculated that. So now with those two, this current base and the Z base is determined. We know that. Okay. So how do we now draw the per unit circuit diagram? Well, this voltage is 480 angle 0. the base value, this is the actual value, the base value is 480. So then this is going to be 1 angle 0. Generator is going to be 1 angle 0. Okay? We don't need to draw transformers anymore because circuit referred to the primary or secondary is the same. Per unit parameters don't change. So these impedance values, 20 and J60, what is their per unit value? The base impedance is, we know the base impedance on the transmission line. We divide the actual by the base, we get the per unit values. And same can be done on the load side. So the equivalent circuit is going to look something like that, 1 angle 0. Transformers disappear because we don't, the circuit referred to the primary and secondary is the same. So in region 2, so to the left of this first line on the left is region 1. In between the two lines, region 2. Right of the rightmost line is region 3. Okay. We have the per unit values. And we have a simple circuit now. Transformers have disappeared. We can calculate current. Right? So the in the per unit circuit, right? The current that flows everywhere is the same in all regions. Yeah? All regions the same current flow because it's one current that we compute. The per unit value of the current. But the actual value of the current, if you want to know in a different region, you know how to do it. Actual value will be, you take the base value relevant to that region, multiply by that, the per unit, and then you'll get the actual value. Right? Because the three regions have different base currents. So although the per unit value is the same, the actual value will be different for the three regions. Right? Yeah? So you can see the circuit is much more simplified. It's a simple circuit we have when you do a per unit circuit diagram. And then you can calculate all sorts of things. You can calculate the loss in the transmission line. You take the line current magnitude, square that, multiply by the resistor, right? And then the value you get is a per unit value. I squared R is per unit value. The I squared R, the per unit value is this. Okay? This is the per unit value. Then I want to know the actual value. I know the apparent power base. I multiply by the apparent power base, which is that, to give me that many watts. Right? And then if I want to know what's happening in the load, same thing. I have the I squared R loss in the load, multiplied that by, well, that's the per unit value. Well, this is the load we are talking about. Multiplied by the, per unit value by the base, and you get that. See, if I want to know the current, right? So the current in the current flowing in the power system, well, that's the current, same current flows everywhere. That's the per unit value. But if I want to know what is the actual current that's flowing in the load, I need to take the base value relevant to this region, multiply by the per unit value, and have the actual value. Right? Clear? All right, so that's some discussion about the per unit system. So I hope the understanding for you is clear, but there will be more questions in the tute that will go more deeper, and you will develop a deeper understanding. Right? There will be questions on changing the base. Right? This is the fundamental. So there will be questions on changing the base, and you will be able to understand, comprehend that. And the tutorial questions will be a little bit more difficult, but you will be able to comprehend, understand based on this fundamental I'm talking about. Because when you know the fundamental, the base, you can understand something more complex. All right. So here, we talk about three-phase transformers. So what do? What is we know a transformer? You have a primary coil, you have a secondary coil, right? You just have two coils. So a three-phase transformer, you have a primary coil on one of the lines, one of the phases, phase A, let's say. There will be another primary coil on phase B and another primary coil on phase C, right? Because we have three active lines. And those can be connected in a Y if you like. Those three primary coils can be connected in a delta if you want. This is possible, right? And for the secondary coil, it's the same thing. Instead of one coil, you can have three coils. They can be connected in star or delta. So we have now various possible combinations. The primary three coils can be connected Y, secondary three coils can be connected in Y. Primary three coils can be connected in Y, secondary three coils can be delta. Primary three coils can be delta and secondary three coils can be Y. Or primary three coils can be delta, secondary three coils can be delta. So those are the possibilities. Okay? Now, the key point is this. You have a primary coil, you have a secondary coil. The number of turns in the primary coil over number of turns in the secondary coil is the turns ratio. Nothing else. Yeah? The voltage across the primary coil, voltage across the secondary coil, irrespective of what is the connection type, voltage across the primary coil over voltage across the secondary coil, V1 on V2 is the turns ratio A. Yeah? It's nothing else. So, you can see this equation. Here it says turns ratio is V phi P. In other words, the phase voltage for the primary, phi is phase. Phase voltage for the primary over phase voltage for secondary. Now, what is the phase quantity? Do you remember what is phase? What does phase mean? Phase voltage, phase current. What does phase voltage mean? Line to neutral. What if there is no neutral? No. It is line to line, but when you say line to line, you are talking about a voltage only, right? Isn't it? You are talking about, when you say line to line, you are talking only voltage. But when you are talking about phase quantities, your answer is partly right, because for voltage, yes. But if you are talking about phase quantities are applicable for voltages and also currents, isn't it? Because there is phase voltage, there is phase current. So what does phase mean? Sorry? Yeah, I think I know what you mean. Anybody know what phase quantities mean? Phase means across the element or through the element. Because imagine you have voltage sources or impedances, right? So the voltage sources or impedance, let's talk about impedances. Doesn't matter. These can be voltage sources too. Phase quantities means the current flowing through this element or the voltage across that element. Phase means through or across the element. That's all phase means. Okay? So here you're talking about the primary coil and the secondary coil. So it's a voltage across a coil in the primary, voltage across a coil in the secondary. If you take that ratio, is the turns ratio. And that makes sense, right? Because that's how the transformer works. In the single phase, I mean, you have a primary coil, you have a secondary coil, and the ratio of that is the turns ratio. Ratio of the voltage is the turns ratio, N1 on N2. So this equation hopefully makes a lot of sense to you. Because if I take the voltage across the primary coil, voltage across the secondary coil, I take the ratio, that's turns ratio. This is phase quantity because it's across a particular element, across the coil. Okay, so now let's look at what is written here. Now on the left hand side, what are we looking at? We're looking at line to line voltages on the primary side and line to line voltage on the secondary side. Okay, now if we are talking about star to star connection, Y to Y, line to line connection would be, line to line voltage on the primary would be root 3 times the phase quantity, voltage that appears across the primary coil multiplied by root 3. Same can be said about the secondary. Line to line secondary voltage is the voltage across the secondary coil multiplied by root 3. So the ratio of line to line voltages in the primary and ratio of line to line voltage in the secondary is the turns ratio, is also the turns ratio for Y-Y connections. Right? For Y to Y connection is the same. And then you take Y to delta, Y, okay, like you have the primary coils connected in star, right? So the line to line voltage on the primary is root 3 times that phase value in the primary. Secondary is connected in delta. So the line to line voltage is the same as the phase voltage for the secondary. So the ratio of line to line in the primary to line to line in the secondary is root 3 times A, and the explanation is there. Right? And the explanation is there. It's the same. Yeah? Does it make sense to you all? Yeah? Or you're not sure? Because V phi P, what is V phi P? V phi P is the voltage that appears across the primary coil on the primary, yeah? And voltage that appears across the primary coil, I circled that. But then the line to line voltage is root 3 times that voltage. Yeah? In a star connection, line to line voltage is root 3 times the phase voltage. You know that, right? And the secondary coil is connected in delta, and the voltage that appears across the secondary coil, which I've circled in blue, is the same as the line to line voltage. Right? So the ratio of the two line to line voltages in the primary and secondary is root 3 times V phi P over V phi S, and V phi P over V phi S is what we call the turns ratio, A. So if I want to take now the ratio of line to line voltages in the primary and the secondary, it's root 3 times A. It's simple. But the transform operation never changes, right? Because you have a primary coil, you have a secondary coil, and the ratio of those two coils is the turns ratio. So you think about phase A on the primary, you think about phase A on the secondary. That's a simple circuit. So this kind of picture in your mind is needed. And so that these equations make sense, right? These equations will be given to you in a formula sheet. But if you don't have a picture in the mind of what it means, it doesn't make too much sense. Yeah? So then this also makes sense to you now, right? Same thing. You just look at line to line voltages in the primary and the secondary, and the phase voltages, there will be a root 3 factor associated with those, and then the turns ratio is as shown here. And same thing can be said about delta. So the line to line voltages and the phase voltages are the same, and the turns ratio is just same. Right? So the turns ratio, I go back, turns ratio is not related to line. Well, it's actually turns ratio A is actually that equation, but it's related to line in based on the configuration. It's connected. Based on configuration, it's connected. Right? So that's 3-phase transformers for you. So I want to get to the end of this chapter 3, then we take a break and we start chapter 4. Right? This is 4:12, so we continue. Okay, so we have three-phase transform example. 50 kilovolt amp, so that's the three-phase power, right? 50 kilovolt amp. 13,800, 208 delta Y distribution transformer has a resistance of 1% and a reactance of 7%. So this is per unit values, right? 1% means 0.01, 7% means 0.07. So this is in per unit. Now only two values are given. So how would you imagine the transformer equivalent circuit now? Because you're only given two values. You're given resistance and reactance. So how are you imagining the circuit, transformer circuit? Without the shunt, just a series branch. You're absolutely right. Without the shunt, just a series branch. Right? So you have a resistor and an impedance. So sometimes a transmission line is also like short transmission line. What is the equivalent circuit for that? It's just the series branch, resistor and impedance. Sometimes we even disregard the resistance because the inductance is greater than the resistance. So sometimes transmission line is just the inductor. If it's a short transmission. Yeah. But of course we have the pi models and the modifications that you do to the pi parameters if it's a long transmission line. Right? That's what we have. Okay, what is the transformer's per phase impedance refers to the high voltage side. Calculate the transformer's voltage regulation at full load and 0.85 factor lagging. Calculate the transformer's voltage regulation on the same conditions using the per unit system. So given these per unit values, we need to find the actual values is the first question, right? Refer to the high voltage side. Secondly, using those actual values, what is the voltage regulation, right? Third question is asking you to find the voltage regulation using not the actual values, using the per unit values. So that you will appreciate the calculations based on per unit is simpler, right? That's the purpose of this example. So you calculate the actual values, refers to the primary. You calculate the voltage regulation using the actual values. Then you can do the same calculation, voltage regulation calculation using the per unit values. Is the question. Okay, so high voltage side of the transformer has a baseline voltage of 13,800. Right? That's the base value on the high voltage. The base apparent power is 50 kilovolt amp. That's given to us. Yeah. Since the primary is delta connected, this equation holds. Right? You can derive that equation. It's delta connected, so remember we actually did the calculations. S base would be, if it's phase values, 3 times V B I B, right? It's for phase values, right? Using the phase values. If that's a phase value, that's a phase value. So then you can actually come up with this because Z base is V base on I base. So using these equations, these two equations, you can actually get to that equation by substituting. Yeah. So we know that this base value for the phase value for voltage base, because it's delta connected, is actually this value here. Is that value. Right? So you can make those substitution. This value here is this value. Right? Then you can calculate Z base. And then per unit value for the line is given 1% and 7%. So then we can calculate the actual values for the line by multiplying by the base values, base impedance. Right? Yeah? And then the base value for current again comes from this formula. If I divide S base by 3 and VB, I get I base, which is that. So we can calculate the I base value, right? And you know this equation, transform equation. The voltage that appears across the load, this is the voltage drop across the series impedance, must equal the voltage at the terminals of the transformer, input terminal of the transformer. So A times phi s, the rated value, rated voltage is referred to the primary side, right? You take the secondary voltage referred to the primary side is A times Vs, is 13,800 angle 0, right? Because the transformer is 13,800 is the rated voltage. So if you take the secondary load voltage referred to primary, that's what it is. This is what it is. I phi, it's this current, and we've given it's 0.8 power factor lagging. So it's the angle is that for the current in the load. 0.8 power factor lagging is the load, and this is the actual value of the transmission line impedance, which series impedance, which we just calculated. So so we have V phi P, we have determined V phi P. Okay. Now, what is the voltage regulation? So the voltage regulation is going to be this figure, right? 1,506 minus 1,300 and 13,800 divided by 13,800. No load minus full load on full load, right? That's the voltage regulation, which is that, which gives you 5.1%. Yeah. Now, if you were to do this calculation using per unit system, okay, here is the transformer impedance 0.01, 1%, 7%. That's the load. Voltage across the load is the rated voltage, so 1 angle 0. Rated voltage is 1 angle 0. We calculate the current. Current is the rated current, so it's 1 angle something, right? Rated current flows through that, 1 angle something, and this angle is 0.8 power factor, so the angle is negative of that. So now we can calculate V phi P. V phi P can be easily calculated. We know the current, right? We know these impedances. We can calculate the current, which is, yeah, and then we get this. So then what is the voltage regulation? 1.051 minus 1 divided by 1, which is the same answer we got previously. So I'd like you to pay special attention to this example. Make sure you fully understand. You can do the questions, right? Question. Do it both ways, per unit system and the actual values. Just fully comprehend that you understand the calculations that are there. But we use the basic circuit equations when you calculate the base values and the actual values. Right? So then I want to wrap up this by just talking a little bit about auto transformers. Auto transformers share the same primary and the secondary windings. You can see in this diagram. Primary winding and the secondary winding, there is no isolation in the auto transformer. So then you can say V1 on V2 is N1 plus N2, right? In the primary. N1 plus N2 is the number of turns in the primary. N1 is the top coil, N2 is the bottom coil. N1 plus N2. And then secondary is just N2, so V1 on V2 is N1 on N1 plus N2 over N2. So that's an auto transformer, just shares the primary and the secondary windings. There's no electrical isolation, so that's one of the disadvantages. What is one of the advantages? Because you share the primary and secondary, it's cheaper to build because you use less material, right? Less material. The other type of transformer that exists is a phase shifting transformer. So instead of voltages changing from primary to secondary, we change the phase angle. Why do you want to change the phase angle? Because then you can restrict the amount of power that will flow through the transformer. Because if you have 2 points and inductor connected, the amount of power that flows from one end to the other depends on the phase angle difference. Right? So they are phase shifting transformers. So I would ask you to, this is just a picture of a phase shifting transformer, something very large. You can just, for your general knowledge, you can read a little bit more on that on the net. Right? So these things exist. And the other one that you have is tap changing transformer. What is a tap changing transformer? You can change the number of turns on the secondary, right, manually or electronically, so that you can change the voltage that appears at the secondary, generally plus or minus 10%. So say your input voltage is fixed, but you still want the secondary voltage, you want to adjust it. Then you can change the tap position. By changing the tap position, you can change the voltage by plus or minus 10%, roughly. Tap changing transformers. Right. So that brings us to the end of chapter 3. I think we should take a short break, maybe 10-minute break, and then we'll continue. Okay?
Well, I'm sure you could have tried to figure it out by the name. Well, then again, that's not fair.
All right, I think perhaps we can make a start. So we have completed chapter 3. So we are up to chapter 4 now. And chapter 4 is on power system analysis. So what do we intend to do here? We want to analyze a complex power network. So what does a complex power network look like? So let me go forward a few steps. So this is before I show something completely complex, so let me see if I can show you something a bit simpler. Okay. So let's take a look at this. So we could say that this is a simple power network. So this power network has 2 generators, right? So you have a node, number 1, which we could call a bus bar. So generator 1 is connected to bus bar 1 or node 1. Generator 2 is connected to bus bar number 2. Then we have a load connected to bus bar number 3. That's that arrow represents a load. We're drawing some power out. Right? Generators will inject power into the bus bar, into the node. Loads will draw power out of the node. So a load is connected to bus number 3 and it's taking power out of that. And we have bus bar number 4. Neither a generator nor a load is connected to that. So what is connected is some transmission lines are connected. Yeah, some transmission lines are connected. So you can see the different bus bars are connected. The transmission lines connect different bus bars. Bus bar 1 connects to bus bar number 2 through some transmission line. There is a transformer there. And you know a transformer can be modeled with a resistor and an inductor, the series resistance and the inductor if you like. And the transmission line can be modeled with a resistor and inductor if it's a short transmission line, right? Yeah. So the equivalent circuit for a transmission line is simply, even if it includes a transformer, can be a resistor and inductor, can be, if you are thinking about a circuit. Same can be said, bus bar number 1 and 3 connects, a transmission line connects bus bar 1 and 3. Same can be said about 2 and 4 and 3 and 4 as well, right? You can see the connections. So you know, when you look at this, you kind of know how, well, you know the circuit topology, how the network is connected, where the generators are, where the load is. So the idea behind power flow analysis is we want to know the voltages and currents in this network. We want to know what current flows in different transmission lines. We want to know the voltage at different bus bars, different nodes. We want to know the voltages. Right? We want to know the currents flowing in the various transmission lines. Why? We don't want to overload these lines because these transmission lines will have some specifications associated with them. There will be a certain maximum current that it can handle. Right? We can think about current flows in the lines. We can also think about power flows in the lines, because if current is flowing in a line, then obviously there is power flowing as well. We'll talk about what power flow means. Current flow, you know what current flow, well, it's measured in amps, right? So power flow, we know power dissipated in elements. Power generated in an element, we know that. We haven't talked about power flow, but well, if current is flowing, the power can flow as well. So we'll talk about that. So we want to know, current flows in line, power flows in line. We want to know the voltage at bus bars, right? Various bus bars. So power system analysis is about determining all that. So to determine those things, we need some information. Right? Because without information, we can't determine some other information that we want to know. Just like if I want variables x and y, if I want to determine the values of variables x and y, I need to know how x and y are related. At least 2 equations are required. If you're thinking about a linear relationship, we need 2 linear equations to solve for 2 unknown variables, x and y there, if it's in terms of x and y. So likewise, we need to write some equations. There are some variables that we need to know, right? We want to identify. We need to know some information to be able to determine other information of interest. But what we are looking at here, we want to know voltages at various lines. We want to know various nodes, currents flowing through different lines, power flows, how much active power the generators are injecting, how much reactive power they are injecting, how much active power, reactive power the loads are consuming. This information we want to know. And knowing this information is important because we can then ensure the network that we have will work reliably if those currents and voltages are within specified limits. If those voltages and currents are not within specified limits, we know the network needs an upgrade. We need to do something about it. Yeah? Because all of a sudden, let's say that should be maybe a residential bus bar, right? And you have a large number of people coming and settling in a given region, then the power consumption there increases, and then the current flow in line 1 to 3 might increase. And then when that happens, it might exceed the specification. Then as a power engineer, electrical engineer, you know we need to do something about it, because otherwise the reliability is compromised. Yeah? So in this chapter, we're going to look at power flow analysis. Now, this is a more complex. You can see the dotted, the purple bars, they are the bus bars, right? You can see there are a large number of bus bars. This is a bit more complex network. Power system that we have in the Southwest Interconnected System, it will be a number of, even more complex than what you see here. There will be a large number of bus bars. And there are so many generators connected to different bus bars. There are so many loads. You can see power is being, the arrows, power is being drawn by at different bus bars. Right? So we want to find a way to analyze a circuit network like this. And that's power flow analysis is about that. And with power flow analysis, it's a steady state analysis. In other words, things are constant. So we assume the power drawn in particular node is a known value, is some amount. Power generated, active power, reactive power injected into the load is some amount. So we assume fixed value, steady state. But we know the electrical network, I mean, those fixed values can change from time to time. That's okay. Right? So it's a steady state analysis. Power flow analysis is a steady state analysis. So this is what we are looking at. So you have an idea what we are trying to do here in this chapter, why we need to do. So we have a complete understanding of the voltages, current flows, whether they are within specifications. We can plan the future network based on future load demands that will happen in the network and so on. Okay? Okay. So, successful power system operation under normal balanced three-phase steady-state conditions require the following. The generation supplies the demand plus losses. So for reliability, we need the supply to match the demand plus losses. The bus voltage magnitudes remain close to rated values. Generators operate within specified real and reactive power limits because generator has a certain capability, active power capability and reactive power capability. So we want to make sure generators are not stressed. They are within the specified range. They're operating within the specified range. Transmission lines and transformers are not overloaded. We want to make sure they are not overloaded because if there is excess current, it could be, safety could be compromised. It could be fires because I squared R is like heat dissipation. So we want to ensure a successful power system will satisfy these kind of criteria. Power flow analysis, sometimes called load flow, is a basic tool for investigating these requirements. We can investigate these requirements. Most common power flow system analysis tool is the power flow, also known as load flow. Power flow determines how the active power and reactive power flows in the network. We'll talk about what that means. Also used to determine bus voltage magnitudes and angles. So you want to know the bus voltage magnitudes and angles. Power flow is a nonlinear analysis technique. Power flow is a steady state analysis tool. Okay, there are various load models. So like I showed you in the diagram, there's an arrow. So there are various models for a load. The load can be represented by a constant impedance, if you like. So there can be a constant impedance model. So in the notes there is this Z star was missing. And then S can be computed. S is the complex power, can be determined based on that formula. right? Based on that formula, you can determine the complex power, magnitude of the voltage square over Z conjugate. The Z is the constant impedance load. The load, I mean, a load can be represented by a constant impedance. But a load can also be represented by not just a constant impedance, by the power it draws. So you can say a load, I'm not going to model it as a constant impedance. I'm rather going to model it as a drawing certain amount of active power and certain amount of reactive power, consuming a certain amount, P and Q. So if P is positive, it's consuming active power. If Q is positive, it's consuming some reactive power. If Q is negative, on the other hand, it's generating some reactive power. Because we know load can also generate reactive power. If it's a capacitor bank, it can generate reactive power. But of course, its load is always going to consume active power, and the notation that we are, sign convention that we are going to use is a positive sign for P and Q, means a consumption. Right? So what I'm trying to say here is we can have a constant power model. In other words, we tell what is P, we tell what is Q for the load. We don't tell the impedance. If you tell the impedance, then that's a constant impedance model. Right, linear and nonlinear power system models. Engineering models depends on the application. Generators, we generally use two different models. A steady state model, right? A steady state model treating generator as a constant power source operating at a fixed voltage. This model will be used for power flow and economic analysis. So we can have a model for a generator. Then the model for a generator, just like model for a load, can be how much power, active power it consumes, how much reactive power it consumes. Model for a generator can be how much active power it injects and what is the magnitude of the terminal voltage of that generator. That's a model for a generator. Yeah? We could have that model. A short-term model treating the generator can be a voltage source behind a time-varying reactance. So if you can also model a generator as a voltage source behind a time-varying reactance, that's another type of model that you can have. But a steady-state model would be a constant amount of power injection into a bus bar, and also what is the voltage magnitude at the bus bar. That's a model for generator. Right. Linear power flow systems. So if you're talking about linear power flow systems, we know voltage across a resistor and a current through a resistor is related to by V equals IR. Voltage across the inductor, impedance of the inductor times the current. And same can be said about the capacitor. So the voltage and current through these elements, three elements, resistor, inductor, and capacitor, are linearly related. So if you have a circuit like this, because of that linear relationship between voltage and current, if you have a circuit like this with just two voltage sources or current sources in there, we can use superposition because voltage and current are linearly related. And if you write Kirchhoff's voltage law, they are linear equations. We can use superposition to analyze the circuit. In other words, we can treat all the sources, we can turn all the sources off except one source. You can see its effect on the network, and you can do for all the sources like that, and you can sum the effect of all the sources to find the combined total effect. That's superposition. So that's a linear model. Non-linear model for the circuit, we don't model the power source as a voltage source. Instead, we tell how much active power is injecting, magnitude of the voltage source, loads we can model as consuming active power, reactive power. So we talk in terms of P and Q, and P and Q, P is the product of voltage and current, so we have now a nonlinear relationship. So that's a nonlinear model, right? So in power flow analysis, if we are going to talk about, describe or model generators and loads using power, active power and reactive power, then we have a nonlinear set of equations to solve, not a linear set of equations. So I said the power of load flow is a nonlinear analysis technique, right? A nonlinear technique. And the reason why it's a nonlinear technique is because we are talking about, or we are specifying power, active power, reactive power, instead of specifying just voltage and current only. Because in a normal circuit that you analyzed in your previous years, you had voltage source magnitudes, current source magnitudes, you knew, you have the impedance values, they are linearly related, it's a linear model, so you could use superposition and other techniques, linear techniques to solve that. Now we are modeling using power, active power, reactive power, so active power, reactive power, product of voltage and current, therefore we are going to end up with nonlinear equations, and we need nonlinear techniques to solve these equations to determine the parameters that we want to determine. Okay? Now, what is the power flow problem? So we need to, like if we want to gain an understanding of power flow, the questions that we want to answer, we need to know what the problem is, right? Because if you don't know the problem, we don't know what we are answering. Right? So what is the problem? So this is the problem. A power system configuration for a given power system configuration. So we know the configuration of the network, where the generators are connected, where the transmission lines are, where the loads are. So that's the network configuration. Given a power system configuration and partial information of each bus bar. So each bus bar, there is certain amount of information that it can have. If we have partial set of information, a power flow problem is to find out voltage magnitude, voltage angle, active and reactive power at each bus bar. So we want to know voltage magnitude, voltage angle at a bus bar. We want to know active power and reactive power injected into each bus bar. P and Q injected into each bus bar. Okay? So I will talk a little bit more about that. So if let's look at this, I'm still trying to define the problem to you, right? What is the power flow problem? I'm still trying to define. So say that you have a network configuration like this, a very simple one, right? So you have generator connected to bus bar 1, you have a transmission line connecting bus bar 1 and bus bar 2, and you have a load on bus bar 2. So very simple. So there are 4 quantities of interest for each bus bar. Okay? There are 4 quantities of interest. What are the 4 quantities of interest? The active power injected into bus bar 1. So you can see generator 1 is injecting power into bus bar 1. Okay? So when I talk about P and Q, it's what is like from external. You have the network in the middle, right? So think about some external device injecting power. So that P and Q are the injections into that, right? And then on bus bar 2, again, what P and Q are what it consumes. Well, in that case, the injection is negative, it's a consumption there, right? It's the opposite direction, but essentially the same except a sign change, right? So that's P and Q. That is of interest for a particular bus bar. Another 2 parameters of interest for the bus bar is magnitude of the voltage at that node and the phase angle at that node. So it's 4 quantities of interest. Now, for each bus bar, we said there will be some partial information available. So out of these 4 quantities, 2 will be known. Okay, out of the 4, 2 will be known. And the other 2 unknown. So we need to determine those unknown for each bus bar. So if I take, for example, the generator bus bar, generator will be modeled with P that it injects and the voltage at the node. So P and magnitude of V will be known for generator bus bar. So if P and magnitude of V are known, we will actually call that bus bar a generator bus bar. We call it a generator bus bar. So those two parameters will be known. And the other two parameters are unknown, we need to determine. Say a load, with the load we will know the P and the Q that it takes out or it consumes. So we will call that a PQ bus bar because we know the P and Q, or we could call it the load bus bar. We'll call it a load bus bar. Okay? So you know now two classifications, right? There can be generator bus bars, there can be load bus bars. Each of those bus bars will have two quantities of interest. We know the network configuration. We want to find the information that is missing. The two parameters that are not specified for each of the bus bars we need to determine. That's the problem. Right? That's the problem we are trying to solve. Now I'll tell you how we might be able to solve it. If there are two parameters of interest for each bus bar that we don't know, then to determine those two parameters we need to write two equations. Right? Yeah? So what are the two equations that we will write for bus bar 1? The power that is injected must be equal to the power that is flowing on the transmission lines originating from that bus bar. Active power that is injected externally into the bus bar must equal what flows out in the transmission lines. Yeah? That is connected to bus bar 1. In this case, there is only one transmission line connected to bus bar 1. So what is injected will flow in that. Active power. Same thing can be said about reactive power. What is injected, reactive power injected into the bus bar externally must equal the reactive power flowing in the transmission lines. These are called power balance equation, active power balance equation, reactive power balance equation. So for each of the bus bars, you can write the active power balance equation and reactive power balance equation. So you have two equations you can write for each bus bar. There's two variables of interest for each bus bar. So you should be able to solve this. Yeah. So we have bus classification. So if we said if P and magnitude of V is known, it's called a generator bus bar. If P and Q are known, it's called a load bus bar. Right? If we know the V and the angle is 0, we choose, and that's called a slack bus. That's our reference bus. So reference bus, we will know the magnitude of the voltage for the reference bus, and we will know the angle. We don't specify P because we know the power in the entire network, the supply and demand has to be balanced. Well, demand includes the losses as well, right? So P, V and angle is specified, so that is what will take up the balance of power that is needed to, to balance the whole thing. Because in some of the generators, P are specified, right? But then load determines the total consumption. So the requirement, the balancing will happen from the reference bus, the slack bus. So slack bus is a large bus that can supply any amount of active power and reactive. A slight headache. That's fine. Right. So, yeah. So we have a bus classification. We have three types of buses, right? We have a slack bus, we have a generator bus, we have load buses. And for each of those, 2 out of the 4 parameters of interest will be known. And the slack bus is a bus that can provide any amount of P and Q to make the equations work. The total active power and reactive power can be balanced using that. And for other generator buses, P and V will be known. Load buses, P and Q will be known. So now you know the load flow problem. What is the problem we are trying to solve? You know. You know for each bus bar there are two parameters of interest that we want to determine, and you know to do that there are two equations that you can write, active power balance equation and reactive power balance equation. Active power balance equation tells you the active power injected from externally into the network must equal what flows in the transmission lines. On a load side, it's what takes out must equal what flows in, both active and reactive power. Right? Yeah? Yeah. So I think I have said what it is. Yeah. Okay. So here is a picture, right? So we have buses, right? How many buses are there? 4 buses, right? And what are the types of bus? Bus 1 is a swing bus. So V and theta will be known. Theta by default is 0, right? V and theta known. Unknown is P1 and Q1, how much it injects. Bus 2 is a generator bus. So magnitude of P and V will be known. Theta and Q unknown. Q is how much reactive power it injects. We don't know, right? 3 is a load bus. So P and Q are known. V and theta unknown. 4 is a load bus. P and Q are known. And what is the P and Q value for that? Bus 4? 0. Both 0 because there is no arrow. Nothing is taken out. So, yeah. So you can see some power will flow into that bus and flow out of that bus inside the network. So it will be balanced, right? So if power flows in here, the same will flow out here. Yeah? Nothing injected from externally. Right? So that's it. So you know what the problem is, right? We know the configuration, we know some partial information. 2 out of the 4 parameters of interest will be known. The other 2 need to be computed. You write active power balance equation, reactive power balance equation. Those are for each of the nodes, and you have as many equations as unknowns. Therefore, you can solve it. And those equations will be nonlinear. We'll have to use nonlinear technique to solve it. And that's the power flow problem, load flow problem. So at least now you know the problem. So now that we know the problem, we can try to solve it. Right? Because we shouldn't try to solve it without knowing the problem. So we know the problem, so we can solve it. All right. All right, so before I talk about the solution, right, I need to present you some information before I talk about the solution. You know the problem, but before we solve it, I need to present some information. So what is the information that I need to present to you? We need to define what we call a Y matrix for this network configuration, Y matrix. So it's also called the admittance matrix. For a network, admittance matrix for this network. All right. So, take a look at this circuit on the right. Right? That's node 1. We are looking at node 1. The generator is injecting current. That's I1. Yeah, and there are 2 transmission lines connecting bus bar 1. Bus bar 1 connects to bus bar number 2. So we can define current I12, current that flows from bus bar 1 to bus bar 2. We can define bus bar 1 also connects to bus bar 3. So we can define current I13. So you know the notation. I12 and I13 are the currents that are flowing in the network. Yeah, in the network. So current I1 is the current that is injected externally into the node, into the bus bar, right? So if the subscript, if there are two subscripts, that means there are currents that are flowing inside the network. If there is one subscript, well, if we have more than 10 bus bars, it will have two subscripts, but you know what I'm trying to say, right? You know what I'm trying to say. So assume it's got less than 10 bus bars, right? So I1 is the current that's injected externally into it. Yeah, okay? So I1, we know Kirchhoff's current law, I1 must equal I12 plus I13. You know that. That's Kirchhoff's current law. So assume that the admittance of this, well, this is not assume, this is notation as well. Admittance of the line connecting bus bar 1 and bus bar 2 is Y12. Y12 is the admittance of the line. That line has a resistance and a reactance, right? So that has some impedance. That line has some series impedance. You can then convert that to an admittance by taking the inverse of the impedance. Inverse of the impedance of the line is the admittance. So the admittance of the line connecting 1, 2 is Y12. So then the current I12 is the admittance Y12 times the voltage difference between the nodes V1 and V2. Ohm's law, right? Ohm's law. I12 is Y12 times V1 minus V2. So same thing can be said about I13 is Y13 times V1 minus V3. You agree with that? Yeah? So now we can say I1 must equal I12 plus I13. We can write in terms of the voltages and admittances of the lines. So then it simplifies to this equation. This equation here. I1 is Y12, Y13. So let's look at what Y12 and Y13. Y12 is what? Y12 is the admittance of the line connecting bus 1 and bus 2. Because when you are talking about I1, we are thinking about node 1, correct? Current injected into that node 1. So node 1 has two lines connected to, two lines originate from node 1, right? 1 to 2 and 1 to 3. So here is the sum of the admittances of the lines connecting bus 1. Y12 plus Y13. Sum of the admittances. Right? Times the voltage at node 1, V1. Right? And then it has V2. And you have the negative of the admittance connecting 1, 2 times V2. Negative of the line connecting 1, 3, Y13 times V3, right? I'm just trying to give an interpretation of the coefficients in that equation. But how you end up with this equation is just basic Kirchhoff's current law. I mean, I showed the equations where it came from. Okay. So now, if I write I2, so what is I2? I2 is the external injection of current into node 2. So we need to be, see, when we look at these symbols, we always need to have a picture. Otherwise, it doesn't make any sense, right? I2 is the external injection into the node 2 from generator 2. So if I then think of node 2, then I need to look at all the lines that are connected to node 2, right? Node 2, 1, no, bus 1 connect to 2, bus 4 connect to 2. So I take Y12, Y24 and I admittances and I add them. And it's a positive, right? Because I'm multiplying that by V2, node 2. Then the term that gets multiplied by V1, right? I'm thinking about node 2. So it's the negative of the admittance connecting 1 and 2, right? Times V1. And then node 2 also connect to node 4. I take the negative of the admittance connected to Y2 and 4, Y24 multiplied by V2. So just to summarize, it's very simple. let's put all these equations in a matrix. So on the left hand side you have I1, I2, I3. May I ask what I1, I2, I3 means? Sorry? No, I1, I2, I3. It's the currents which are externally injected into the nodes. Right? Currents which are externally injected into node 1, node 2, node 3 and node 4. Not the currents flowing inside the network, right? Yeah. Yeah. Either say. It doesn't matter because it's the admittance. Right? Yeah. So you know what I1, I2, I3, I4 means, right? You know that. Do you? Do you know what V1, V2, V3, V4? What are they? The bus voltages, right? So these currents that are injected into the various nodes must equal to the admittance matrix Y times the node voltages. Okay? V1, V2, V3, V4. Okay? Yeah? So admittance matrix, how does the admittance matrix look like? I mean, this is, we write this using basic Kirchhoff's current law. I explained the first equation, right? I'm now telling you something else, like some other in-depth understanding or about the Y matrix. So along the diagonal, right? So if I look at the 1, 1 element in the Y matrix, I'm thinking about node 1, correct? I'm thinking about node 1. So I need to look at all the lines which are connecting to bus 1 and I sum all the admittances. Okay? We talked about that. So if I look at 2, 2 element, I'm thinking about what? Node 2, right? I need to sum all the lines, all the network lines connecting to node 2 and I sum all the admittances. Right? So node 2, what are the lines connecting to node 2? Bus 1 to 2, bus 4 to 2. So you have Y21 and Y24. Right? If I look at 3, node 3, I'm thinking about bus 3. Again, look at all the lines that are connecting to bus 3, all the network lines connecting to bus 3 and sum all the admittances. And then node 4, do the same thing. Right? Okay? Now, the off diagonal terms. Let's look at 1, 2 element. 1, 2 element means look at the line connecting 1 and 2, the admittance, you negate that and you put it there. 1, 2. 1, 3, right? You look at the line that is connecting bus 1 and bus 3, negate that and put it there. The 1, 4 element, what is the 1, 4 element? It's the line that is connecting bus 1 to bus 4. Is there a line connecting bus 1 to bus 4 here? Nothing. So the admittance is 0. Impedance is infinite, admittance is 0. Right? So you know how to do this now. You know what is the Y matrix, right? How to write the Y matrix you know, and you know how the currents and voltages are related through the Y matrix, and these currents, you know what that means. They are externally injected currents into the node. What are the Y's? V's. V's are the voltages at those nodes. Right? Now, why am I doing this? Why are we doing this? Because in the power balance equations, we want to eliminate current. We don't want the current. So we can eliminate the current using this admittance, this relationship. So the power balance equations will be in terms of the admittance matrix elements and bus voltages. Right? That's the reason why I'm doing this. Okay. I think that is a good place to stop for today, and we'll continue next week.
you all